am Anil Kumar, sharing with you a lesson with my student Akshit. This is on calculus curve sketching. We'll discuss complete concepts to sketch graphs of polynomials, rational functions, and surds. I hope you will enjoy it. You can join my classes by sending an email on the address given. Now, let us enjoy the journey of success. Hi Akshit, how are you doing?
Hi, sir. I'm good. How are you?
Very good, very good. So today, what do you want to learn, Akshit?
Sir, we actually just started curve sketching. So since we started practicing ahead, I was hoping we can go over some examination style questions.
Sure. Since you have started curve sketching at school, I'd like you to go through the whole thing. And in between, I'll take up examples which have come in past test papers. So that way, both the objectives will be met. And this will
Yeah.
be an excellent video for all those who just want to start with curve sketching and understand what it is all about. Okay.
Yeah.
Let me share with you one of the lessons which I have. So can you see my screen?
Yes, sir. I can see it.
Okay. So we'll talk about curve sketching and the algorithm. So
Yeah.
as you can see on the board, we're talking about applications of derivatives. So we have learned all about derivatives so far. We know how to find derivatives of all kinds of functions using different rules, including power rule, quotient
Yeah.
rule, product rule, chain rule, implicit differentiation, right? So all those things we're going to use now in curve sketching. We'll look into the algorithm for curve sketching. That is one of the major things. Now, when we talk about algorithm about curve sketching, I would like to say that you should first understand what type of function it is.
Right.
Based on the type of function, our algorithm will be different. You get the idea?
Yes, sir.
So therefore, what I've done here, I've taken functions which are polynomials, right? Polynomials are continuous graph. Then we have rational functions which have discontinuities, which may
Yeah.
have poles, asymptotes, right? Vertical asymptote, oblique asymptote, horizontal asymptote, all we need to work. And then we have radical functions. Radical functions like the one shown here in blue. Do you see that cusp or corner? Do you understand?
Yeah.
So
Yes, sir.
radical functions are one of the toughest to sketch the graph. And normally that will definitely be a question in your test. When you see
Yeah.
something like x to the power of 2 over 3 or something like that, it means a radical function. Is that clear to you?
Yeah.
It look like what I have highlighted just now. And as you see, we'll have questions which will give you good practice for your exam, test, or quiz, or whatever. Is that okay?
Yeah.
Let's begin with simple polynomial functions, right? So when you say polynomial functions, you know there is no discontinuity. The domain is all real numbers. Range could be from minus infinity to plus infinity. We may have a lot of turning points in between. We may have
Yeah.
point of inflection. That is to say, we may have to check the second derivative for concavity, right? So now
Right.
we'll take up a simple example. As you can see, I am already taken an example which is factored form. One step in polynomial function is that you have to first factor.
Yeah.
Factoring is important. Why? Can you tell me, Akshay?
Yes, sir. Because once you factor, you can find the critical numbers easily, right?
Zeros very easily, right? Main thing.
Yeah.
Right. So the algorithm for polynomials is mentioned right there. Can you please read the algorithm for polynomials?
Yes, sir. Algorithm for curve sketching. Domain and range.
Mhm.
Find the y-intercepts. Find the x-intercepts. Find zeros with orders. Find end behavior. Find the first derivative. Analyze the first derivative for extrema. Find the second derivative. Analyze the second derivative for concavity and the points of inflection.
That's what you do with polynomial functions. Clear? So
Yes,
let's
sir.
get into straight away some examples. So we have one function here, f of x is x plus 1 times x minus 2, right? So that's your function. Now to find the derivative, what you could do is you could use product rule. Perfect, no problems, right?
Yeah.
You could do product rule, no problems. Or you could expand as I've done here, right?
Yes,
Expand and
sir.
simplify and then find the derivative. So many times I've observed that if the function is not very complicated and if it doesn't take much time, as in this particular example you see, right?
Yeah.
Expand and derivative is a better option.
Yeah, because if you use product rule, there's more chance you can go wrong too, right, sir?
Yes, and ultimately you have to simplify that also, correct?
Correct. Yeah.
So therefore, in this particular example, it is a deviation from normal. I have x minus 2 whole square, which I wrote as x square minus 4x plus 4, multiplied by x plus 1, got my term. And then do you see we have only three terms finally? X cube
Yeah.
minus x square plus 4. Very simple expression to work with. You know the y-intercept is 4, right? And then
Yes, sir.
can have a lot of properties. But from the factored form, we did get the zeros for the function and the order of
Yeah.
the zeros, correct? So as I was
Correct.
saying, when you have a polynomial, step number one is to understand what the polynomial main parameters are. So we have the domain, which is all real numbers, range is all real numbers, y-intercept is 4, correct, which we have got here.
Yes, sir.
Intercept is all those zeros, minus 1 and 2,
And two.
along with
Yeah.
order. Order for minus 1 is 1, and order for x minus 2 whole square means 2, right?
Two. Yeah.
So at 2, we have an order of 2. So let me write this in brackets. It's good to write. I've written otherwise, zeros with the order, right? Order of 1 for
Yeah.
x equals to minus 1, and order of 2 for x equals to 2. And then the end behavior. Since we know this is a cubic function, right? It's a cubic
Yeah.
and it is positive leading coefficient. It will start from negative infinity, land up in positive infinity.
Positive.
That is the
Yeah.
end behavior which we have mentioned. So, without getting into derivatives, this is the first information which you get immediately from the graph, from the equation itself. Correct? That gives you fairly
Correct.
good idea about all this. And we have an idea that this will be kind of like this, right? Do you see that? Well,
Yes,
that
sir.
point is turning and the 2, right? So we have some idea.
Yeah.
Now let's, with this idea, move forward. And first thing which we are going to do is we'll find the derivative of a simplified equation. You get the idea?
Yes, sir.
See, imagine now finding a differential of x plus 1 times x minus 2 whole square and then simplifying will take a lot of time.
Yeah.
So better expand, simplify, and then work on it. So first derivative 3x squared minus 6x factor 3x and x minus 2. So now
Yeah.
we have stationary points. So what are stationary points?
Sir, the stationary points are the points where the tangent will be horizontal, right?
0, yeah. Horizontal, correct. So we have learned about two types of points. Let me check with you. One is critical point, right? Critical point or number, we say, right?
Yes, sir.
And when we are talking about a stationary point, what is the difference between the two?
Yes, sir. I think like we discussed, the stationary point, the slope of the tangent would be 0, right?
Yes.
But at a critical point, that's not
Yeah.
necessary.
No. At critical point, the slope of the tangent is equal to 0 or does not exist.
Oh, okay, does not exist, right?
Both. Stationary point, we are only focusing on derivative to be 0. Well, it works well for polynomials. It is smooth.
Yeah.
Right? What is the saddle point?
A saddle point, sir. So would it be both of them in that case?
So do you see this part? It looks like a saddle on the horse, right? So here also,
Oh,
your derivative is 0, right? Correct?
yeah.
And but you see, it is not a maximum or a minimum. It is not a local maximum minimum. Do you see that? It's a point of inflection.
Yeah.
Right? So still the derivative is 0. However, the tangent crosses through the curve. Do you see that?
Oh, okay. So
On
that's
this,
called a saddle point?
yes. If you have a turning point, which is also showing you a tangent at this point, but the curve is either below or above
Yeah.
right? The curve is below or above the tangent, making it a local maximum as shown here, or a minimum if it is the other way. You get the idea?
Yeah. Yes, sir.
So these are 3 points which we always use in our questions. But you should understand them clearly, how they are similar, how they are different. All of them, derivative is 0, all of them, right? But for
Yes,
critical
sir.
numbers, we also look into the points where the derivative does not exist. It is like approaching infinitely large value. As in the case
Yeah.
of, can you tell me example?
A rational function, sir.
Rational functions and also radical functions. You could
And
have,
yeah,
right, at the cusp or a corner, even absolute value function at the corner, the derivative is not defined. But it
yeah,
is a local minimum or a maximum, depending on the function.
correct.
So it's a
Yeah,
critical point. Perfect. Now, coming back to our question, we just found the first derivative of this polynomial, which is 3x squared minus 6s. Factor it so that you can find the stationary point. So when we
yeah,
work with polynomials, we use the term stationary point. But as soon as we start working with rational functions or radicals, we use the term critical point.
critical point.
We are interested in the derivatives does not exit position also. Correct?
Yeah,
You
correct.
can use critical points in general because it is like
Yeah.
for anything. Anyway, can you tell me how do we find maximum, local maximum or minimum from the first derivative?
Yes, sir. So like we did after we found the first derivative, we can equate the equation to 0 from its factored form. And now we get that the critical numbers are 0 and 2, right?
Correct.
So if we make ourselves a plane, it'll divide our plane into three intervals.
Good.
Yeah. And based on the intervals, we can choose a test point and then determine the sign of the derivative.
And determine the sign. So if there are two negatives in this case, we get positive sign, negative sign, positive sign. Positive sign means derivative function
Positive.
is increasing. Derivative positive means the function f of x is increasing. You get the idea.
Yes, sir.
So function increases and negative means function decreases. That means there is a maximum over there, right?
Correct. Yeah.
So we got a maximum at x equals to 0 and local minimum at x equals to 2.
X equals 2.
You have to find the value for maximum and minimum, substituting the value in the function. Is that okay? Because graph is of the function.
Right.
First derivative was only utilized to figure out where is the maximum. You get the idea?
Yeah.
So put it back into the value of the put it back into the function itself to find the value of local maximum and local minimum, and they become very critical points for you to sketch the curve, right? So we already have the intercepts, correct, domain range, and now we have turning points which lead to maximum and minimum. Perfect. Now what we should be doing? From the first derivative, we have to find the second derivative.
Right. For concavity, right, sir?
For concavity, as you can see, then you find the critical points. In this case, there's only one critical point, which is at x equals to 1. And now you check concavity. So what is the rule for concavity? Can you summarize?
Yes, sir. Once again, we just put down our critical number. And in this case, it splits our plane into 2, right? If the second derivative is less than 0, then it's concave down. And if it's greater than 0, it would be concave up.
Perfect. So that is how concave down is. This is concave up.
Yeah.
And we clearly see this. Since the concavity changes, we do have a point of inflection at x equals to 1.
1, yeah.
Now again, substitute all these values in the function to find the y value at all these points, correct?
Correct.
Concavity point we have got now 1 to 2. We have an interval in which the function is concave down and the interval in which the function is concave up.
Concave up.
Now it's good time to summarize all the things together. So on the left side, do you see the algorithm once again written, right?
Yes, sir.
That is how you should be doing in your test paper. Clearly write down everything which you have discovered so far about the function. Can you please read what all did you get?
Yes, sir. We found that our y-intercept lies on point 0.04 and our x-intercepts were -1 and 2. And our zeros with their respective order would be order 1 for the 0 at x equals -1 and order 2 for the 0 at x equals 2. And our end behavior would be as x approaches minus infinity, y approaches minus infinity, and as x approaches infinity, y approaches infinity. And our maximum is at 0.4 and minimum is at 2.0. And it's concave down on the interval from -infinity to 1 and concave up on the interval from 1 to infinity with a point of inflection at 1 and 2.
Yeah. So there you go. It's an accurate graph shown to you. That
Yeah.
is how you do any polynomial for that matter. And that's the algorithm for polynomials. Perfect. We
Perfect.
need not do any testing for asymptotes and holes and
Yeah.
discontinuities because polynomials are continuous graphs. Perfect.
Yeah.
Now it's time to look into rational functions. Perfect. So here I've taken up an example with a rational function. So can you please read what is the function given to you?
Yes, sir. Example 2, rational function. Sketch the graph of f of x equals x squared minus 3x plus 6 over x minus 1. Do not determine the second derivative.
Very clear. You don't really have to. If you have
Yeah.
time, if you have time, if you're
Yeah.
not running out of time, then do second derivative for rational function. Very critical point because many times you are
Yeah.
attempting the question and trying to do too many things, right? And second derivative is not easy for a rational function. Let me tell you, because
Yeah.
already you have degree 4 working
Yeah.
with degree 2 and derivatives. It's not easy. So therefore, without that, actually, you can sketch the rational function most of the time, right?
Correct.
If
Yeah.
the time permits, then only. Or if they say, find the
Yeah.
concavity and show that, then it is a different story altogether. Okay.
Yeah.
Otherwise, if there is no time at the end, because this is normally the last question to be attempted, right? Let's look into
Right.
it.
Right.
Do the best of the time available to you. Perfect.
Yeah.
Now, can you tell, looking at this rational function, what kind of asymptotes do you expect?
Yes, sir. So definitely a vertical asymptote and an oblique asymptote, sir.
So, oblique asymptote, why did you say oblique? Tell me.
Because the degree of the numerator is exactly one higher than the degree of the
Correct.
denominator.
So, numerator degree higher by 1, right?
Yes, sir.
Is equal to denominator degree plus 1. 1 higher means linear, 2 higher means approach a quadratic function. So we have
Yeah.
an oblique, so you'll divide the numerator by denominator to find the equation for oblique asymptote. Clear. Vertical
Yeah.
asymptote, we should first factor the numerator before concluding, right?
Right, because
Because
it may
we have
cancel.
plus 6, right? It might just, who knows, right? So
Yeah.
6 means we could have what? We have minus 3 here. Can you factor it? Not really.
I don't think so. Yeah.
No, you cannot really. So it cannot be factored. So clearly, we have a vertical asymptote at x equals to 1, correct? So we have two critical
Correct.
things from here. Okay. So the algorithm is right there before you. You have to begin with the vertical asymptote, which is there. Horizontal asymptote is not there, but we have oblique asymptote. Can you tell me, can horizontal and oblique asymptote exist same time?
No, sir, they cannot.
Because for horizontal asymptote, degree of numerator cannot be greater than the degree
Yeah.
of denominator. It is either same or less than. Correct.
Or less. Yeah.
Then we find domain and range clearly from the function. We know the horizontal asymptote is not there, but the oblique asymptotes, we'll just wait for maximum and minimum values.
Yeah.
Figure out domain and range. So we'll hold on this, right? Only thing
Yes,
we
sir.
can say in the domain, x equals to 1 is not included. Find the x
Right.
and y intercepts, and once you do this general, then you begin with analyzing the first derivative. Focus more on first derivative. You get to know the graph very easily. So first thing, we have all this information on the left. Can you please read what information do we have on the left side?
Yes, sir. Our vertical asymptote is at x equals 1. We have no horizontal asymptote, and we have an oblique asymptote. Our domain and range.
So we did this synthetic division to find the oblique asymptote, as you can see on the right hand side, right? You're familiar with it. And we got
Yes.
x minus 2 as the oblique asymptote, and plus 4 over x minus 1. Now let's discuss about behavior near the oblique asymptote, right? So before we go further, let me just, because this is a very important key area which we need to figure out. So can you tell me the equation of oblique asymptote after division?
X minus 2, sir.
That means we have a line like this, right? X minus 2, and that's my oblique asymptote. Plus 4 over 4 was the remainder, plus 4. That means if x is approaching positive infinity, means it is positive, then we are adding something to the function, and clearly that means function will be above the line. Is it okay?
Yes,
so it approaches from above. Do you understand? When we do x approaches positive infinity, it approaches from above. So when x is approaching negative infinity, then this value will be negative. we have minus here, so it will approach from below. Does it make sense to you?
Yes, sir. Makes sense.
So when x is approaching negative infinity, in that case, y is approaching from below. And when x is approaching positive infinity, it is approaching from above. Clear?
Clear. Yeah.
Got this. Now, we also have a vertical asymptote, which is at x equals to 1.
Sir.
So let's say this is our vertical asymptote, right? Now,
Yeah.
in that case, we have to figure out its behavior near the vertical asymptote. This is very important, right? So make a note, you have to show behavior of curve, which is that of function, right?
Yes, sir.
Near the asymptote. Sometimes you can just take a value and calculate. You could do that. For example, if you're talking about x equals to 1, you could find the limit when x approaches 0.9, right, of the function. That is, you're checking from left. Is that okay?
Yes, sir.
And you can find the limit 1.1, correct?
Yes. Yeah.
That will give you which side you're approaching, right? So in this particular function, we have the expression given to you. If I take a value of x, which is less than 1, then in that case, denominator will be negative, right?
Right.
So, and the numerator seems to be much higher. So we have approaching negative infinity from this side. You get the idea?
Yes,
Also,
sir.
plug it in your calculator and find. So you get this behavior. Similarly,
Okay.
you get this idea. It is important to mark on the graph. You get 0.5 marks for this, otherwise they are deducted.
Yes, sir.
Right? So you have this. So kind of it is known that the function will be like this. You get the idea? That is why I was saying you don't have to check the concavity, because once you find you have a local maximum minimum, you know the graph will be kind of like this. Do you see that curve?
Yeah.
So we almost made the curve. There is no need to prove that this is concave down, right?
Right, sir. Sir, quick question.
Yes.
So when we draw the oblique rational function, right?
Yeah.
For labeling the points, is it okay if I just label the oblique asymptote and the vertical asymptote, because the graph may not be exactly accurate, right?
No, write down the equation, because that's a very important part, right?
Right.
And so x equals to 1, I've written the equation, right? Of course, you'll write all this. Perfect.
Right.
Label as much as you can. Okay. That is what I will say. And critical points now to figure out is, after the analysis, we have to find the local maximum and minimum. Is it okay? So let's continue. So you can see very clearly that we figured out the behavior near oblique asymptote as well as vertical asymptote, right? You understand how do we figure this out, right?
Yes, sir.
Now let's take the first derivative and analyze it. So here is the function itself. To find the first derivative, you will use the quotient rule. Perfect.
Right.
So as shown here, you use the quotient rule, denominator square, first derivative of the numerator times the denominator minus the numerator and denominator derivative is only 1. So I wrote that expression. Key thing is to simplify and write it in the factored form. Once you have the factors, then you can find the critical numbers. Do you see I'm using the term critical numbers now?
Yes, sir.
We are interested in discontinuities, right?
Yes, sir.
That gives us a very important parameter. How does it approach a discontinuity, which is a vertical asymptote in this case? Perfect.
Right.
Now analyze using the table, take the test points, and we find that the interval is increasing from minus infinity to minus 1, and then decreasing to 1, and then again decreasing till 3, and then increasing. Clearly, we have a local maximum at minus 1 and local minimum at 3. Get 3. And as expected. At both the points, find the y values, substituting the x values in the main function. Now you know local maximum, minimum, and now summarize all your learnings. Very, very important. So write down the summary of the result very clearly at one place before sketching your graph, so that you can clearly see what you got and what you should be sketching for. You get the idea?
Yes, sir.
Otherwise, in last minute, you could do some mistakes, which we don't want. right?
Yeah.
Can you please read the summary on the left-hand side?
Yes, sir. So our y-intercept is at 0.06, and our vertical asymptote is at x equals 1. Our oblique asymptote's equation would be y equals x minus 2, and as x approaches minus infinity, y approaches L, the oblique asymptote, from below, and as x approaches positive infinity, y approaches L from above. Vertical asymptote x equals 1. So when x approaches 1 from the left, y approaches negative infinity. And as x approaches 1 from the right, y approaches positive infinity. And our maximum is at -1 and -5, and the minimum is at 3, 3.
Label your diagram clearly, showing all the intercepts. I wrote the y-intercept as positive. It is -6 as shown here, right? So clearly we have the local maximum minimum points as we decided. Now for yourself, you can see there is no need to find second derivative and concavity.
Yes, sir. Yeah.
When I found that behavior near the asymptotes, right? This is my behavior near the asymptotes, which I have already discussed with you, and the local minimum. This is the only way the curve can be drawn, correct? Similar, on the other side also, that is the way the curve can be drawn, and therefore this is enough. If the time permits, you can go into the second derivative, which normally is not a simple job, since you can see the first derivative itself was complicated. You get the idea?
Yes, sir.
Okay. If it is simple, just do it, right?
Yeah.
Right. Let's move on to the final examination type of test. Can you please read the question this time?
Yes, sir. Example 3, graph of surds. Sketch graph of f of x equals x to the power of 5 over 2 minus 10x to the power of 3 halves.
Now, one of the critical things to work with surds or radicals is factoring. You should know how to factor these. You get the idea?
Yeah.
So when we are going through this solution, focus on factoring and see how we have factored and got the critical numbers. Otherwise, it will be very difficult in the test. Okay?
Yes, sir.
So I like you to just go through the solution very neatly typed, elaborated, right? Can you say function f of x is given to you, right? Which is f of x equals to x to the power of 5 over 2 minus 10x to the power of 3 over 2. Now, we have also mentioned here that x belongs to a real number where x is greater than equal to 0. So we are restricting our domain to only positive part of this, right? So we are doing that restriction on purpose. That's the part of the question. Is it okay?
Yes, sir.
Correct. So that is the question now. Now, origin is a critical number. Since it is an endpoint, we cannot check nature of the graph on its left side while analyzing the first and the second derivative. So as soon as we have a restricted domain, so we are doing two purposes here. Also teaching you what happens when we restrict our domain for the function, right? You cannot find the limit from both the sides.
Right.
And therefore, at the corner, derivative is not defined. Derivative is defined in the open interval of this continuous function, which is bound at 2 points. Not in the closed interval. Remember that, as that will also be a communication question for you. Okay?
Yes, sir.
Very clearly, we just found some very critical points before we begin. So first thing is always find the critical things, right? So looking at the I can of course factor and then figure out. So we have got some critical points easy to work out if x equals to 1 and 0, right? So we got 2 points on the curve already.
Yes, sir.
Now we'll go for the derivative. Well, find x-intercept as we decided earlier, and the y-intercept, you know, it is at the origin itself, right?
Yeah.
So you can factor and find the x-intercept. Now look at the factoring at this side. Can you please read how the factoring has been done?
Yes, sir. So from the given function, we took x to the power of 3 halves common, and then in the bracket, we got x minus 10. So our two x-intercepts would be 0 and 10.
Correct. So x to the power of 5 by 2 and 3 by 2. 3 by 2 is smaller.
Yeah.
Right? So, and 5 minus 3 is 2. So 2 by 2 is 1. And therefore, we got x minus 10 as the other factor. Clear? Once you have this first derivative, you have to analyze just as we did analysis in the previous two cases. No different, right? So once you analyze this, as shown here, we found that there is a minimum at 6. Okay, because the
Yeah.
derivative is shown to you. See how we factor derivative. Do you see that part? Factoring
Yes,
derivative.
sir.
Very important. So x minus 6. So 0 and 6 are two critical numbers for us. Analyzing both of these numbers, you cannot test on the left side of 0. Do you see that part? Blank.
Yes, sir, because it's undefined, right?
Because the domain is being defined to greater than equal to 0. Is that okay now?
Yeah, okay.
We're only testing on the right hand side. We have a minimum, and now there we go. We have a minimum.
Yeah.
Now you analyze the second derivative of the same function. Concavity in this case is very important. You cannot
Yeah.
avoid second derivative. So take second derivative and you find a point, critical point, which is 0 and 2, which again divides the interval. Check for the concavity using your table. You
Yeah.
find that the concavity changes at 2. That means there is a point of inflection at 2, correct?
Yes, sir. Sir, quick question.
Yes.
In our second derivative, right? Would it not be 15 over 4x to the power of 1/2?
Okay. So first derivative is here. So minus 1. There could be an error. Let me just check. So minus 1 will be 1/2. Yeah. 1/2. And here minus half.
Okay, yeah.
Yeah, there is some error there. Correct. Minus half. So this will be minus half.
Yeah.
This will be minus half. And then we do x minus half. Correct. Yeah, there is a good check. Very good check. Okay. So anyway, we have the same critical numbers. Now, once you have those critical numbers, you analyze them. Correct?
Correct.
Yeah, but that's a good check. So correct this. Good job. Perfect. So analysis is similar. The only thing is the derivative could be tricky. And then if
Yeah.
you know how to factor it, you can analyze just as we did previous two functions, which were polynomial and rational functions. Correct?
Correct.
Now you have all the information required, and therefore, what are we going to do? We are going to summarize the information. Very important. We talk about algorithm, but we normally do not summarize the information. We just start sketching the graph moving forward, and that's a problem because sometimes you forget all the things, right? Once you place them at one place, then you remember them all, and then you have to put them on the graph also. Right. So do not give any chances to your teachers for deducting even a 0.5 mark. That's what we intend to, correct? Try to max the paper. Right. So you have the curve here, correct?
Yeah.
And label all the points as mentioned. And can you please read the summary of what we have got?
Yeah. So our domain of f of x would be given to us as x is an element of all real numbers where x is greater than or equal to 0. And our range would be y is an element of all real numbers where y is greater than or equal to minus 58.8. And our x-intercepts are at x equals 0 and x equals 10. And the function is decreasing on the interval from 0 to 6 and increasing on the interval from 6 to infinity. And our local minimum is at 6 and minus 58.8. And it's concave down on the interval from 0 to 2, both included, and concave up from 2 to infinity. And our point of inflection would be 2 comma negative 22.6.
Correct. Now, as far as the concave down is concerned, you may write this as not included also. So many books do not include it. You say they just use open interval. So both are right. So you could use open interval to be on safe side. Not a problem. Correct. So I hope that summarizes and tells you exactly how do you do curve sketching for any curve whatsoever, because you haven't learned exponential, logarithmic, and trigonometric functions yet. Correct. So transcendental functions we'll do next time. Here are some practice questions for you. So
yes, sir.
So these are the three questions which I thought could help you. First two are the rational functions, and those are the links where actually I have provided the solution for these questions also. Okay. And then question number 3 is the radical function. It is very important to do the exercise yourself. Okay.
Yes, sir.
Right. So you could look into these functions, and then again, there is another good question on rational functions where you may be interested in doing all the things, because earlier, as you can see, we avoided concavity test, correct?
Yeah, correct.
However, this particular question, can you please read the question?
Yes, sir. Show full organized solutions to determine the following and use the algorithm for sketching the function y equals x squared over x minus 3. And we have to find the intercepts, the oblique asymptotes, any vertical asymptotes, minimum and maximum points, make a table for the intervals of increase and decrease, points of inflection, intervals of concavity, and sketch the graph.
Correct. Now, if the question specifies you cannot, you have to
Yeah.
provide all the solutions, right? It's a
Right.
simple function also relatively, as you can see, x square over
Yeah.
x minus is relatively a very simple question to work with. And you can do this as a test practice. That will be good for you,
Okay.
right? So here we have a quick solution. Clearly, we have an oblique asymptote since the degree of the numerator
Yeah.
is one higher, right? So we're not getting
Right.
into the thing, but I'm just showing you what all information so that you can check your answer, right? So here we have
Yeah.
done both first derivative and second derivative side by side and analyze them. So once you analyze them, you have all the relevant data and then the graph of the function as shown
Yeah.
in this particular case. So I think with this, we can end our session. So I'd like you to now summarize our learnings about curve sketching. So what do you say now?
Yes, sir. So I think we really tied everything together in this lesson because we took everything that we learned from 4.1 through to 4.4 and really saw how we can maximize our time when solving these curve sketching problems because some can they can be very complicated, right? But I think if we just see for example with the power functions, if we can just know how to factor with those practice problems, then it'll be really easy for us. And also, sir, with the rational functions, I learned another new thing today, where you know how you had the oblique asymptote and then plus the remainder.
Yeah,
Instead of actually looking for the concavity, if we just use the infinity and minus infinity there, then that really makes our job easy, right? So I plan on using that too.
Good, good. So be careful. If you have time, do the second derivative, maybe long.
Yeah.
I'm not saying don't do it, right? I'm only
Yeah,
saying
yeah.
normally students run out of time. So where
Right.
can they cut down, right? The
Yeah.
minimum penalty will be because you got the right curve, right?
Right,
Absolutely
right.
So therefore, the minimum penalty is at that point, which could take a lot of effort. Right?
Yeah.
That is why I'm telling you, right? If you have been asked for finding it, then the time has been allocated for that purpose. So you have that time
Right.
already allocated for the purpose, and so you
Yeah.
can definitely do it within the time frame of your test. So I hope
Yeah.
that really helps. It is kind of very important. I'd like you to just search Anil Kumar curve sketching playlist, and there are many videos there. So
Yeah.
figure out which ones work best for you, so you can do some of those videos. Okay.
Yes, sir.
So we can. Any other questions from you?
No, sir. Everything's clear.
Absolutely clear. So all the best, Akshay. I expect you to get another 100 this time also. Be on the top. That's great. All the best to you.
Yes, sir. Thank you, sir.
Thank you.